Okay, let's start today's class. Two topics today. The first one, now this time, in the last class, we compare two sequences. Now this time, we compare two functions. Take a review about how to compare two sequences. Suppose we have two sequences, x and x1, x2, x3, and yn, y1, y2, y3, and so on. Now the definition is A. If you can find some constant C, there is a constant C greater than 0, such that xn absolute value over yn absolute value less than or equal to C. We don't require this inequality is true for all n, but we require this inequality true for n large enough. For all n large enough, then we write xn is BO of yn. Definition. Now B, if xn over yn, compare the two sequences by ratio. Limit n approaches infinity, the ratio is 0. Then we write xn is little o of yn. Again, to study mathematics, definitions are most important. Okay, always refer to definitions. Okay, some case, let me separate the two parts. Suppose xn is this sequence approaches say this number x star, and the sequence y approaches this number, then this notation yn xn, no, should be xn, then xn minus x star is BO yn minus y star. What this notation means? This notation means xn minus x star absolute value less than or equal to C absolute value yn minus y star for n large enough. This implies that yn is approaching y star, xn is approaching x star, but we have, because of this inequality, so this implies that xn approaches x star is at least as fast as yn approaches y star. If this inequality is true, then the convergence speed of xn is at least as the convergence speed of yn. This is a big O. Now, how about little o? Little o. If xn minus x star is little o yn minus y star, this notation means implies this limit is 0. That means that this limit implies that xn converges to x star faster than yn converges to y star. Do you agree? This is a review about the comparison of two sequences. Now, today, I compare two functions. Topic 1. Topic 1. We have two functions. Let function f and function t be given. Okay, be given. Okay. We write function f is BO function t as x approaches some point x star. What this notation means? This notation means when there is a constant c and a neighborhood of x star such that if you can find some constant c and if you can find some neighborhood, right? Neighborhood, yeah. X star here, right? Neighborhood, okay, neighborhood. Such that absolute value of f over absolute value of g less than or equal to c for all x in the neighborhood. But x not equal to star. Okay, yeah. This notation, BO notation means this. Okay, if you can find some number c, some neighborhood of x star, so that this inequality is true for all the C, all the X in the neighborhood, but X not equal to X star. Then F is BO of G. Okay. Now, how about little o? Similarly, F is little o of G as X approaches X star. Means, okay, a limit F of X over G as X approaches X star is 0. Now let me make some remarks about these two definitions. Okay. Remark here. Remarks. Okay. Number one, it is very important to specify this point X star. Let me write this down. Okay. It is important that we state what point X star of convergence is intended. For example, compare these two functions. Which two functions? Compare X to -2 and X to -1. Compare these two functions. Okay. Okay. If I choose X star to be infinity, okay, then we have X to -2 is little o of X to -1 as X approaches infinity. Why? Because according to definition, little o means this limit. Okay, because X up to -1, X to -1, then the limit X approaches infinity is Okay, let me rewrite this function. This function is X squared. Then it is 1 over X. Now X approaches infinity, then of course this is 0. So as X approaches infinity, X to -2 is a little o of X to -1. However, if I pick X star to be 0, okay, then we have X to -1 is little o of X -2 is -2 as X approaches 0. Why? Because according to the definition, because X -1, X -2, X approaches 0, it is, let me rewrite this function. This function is just X, right? Do you agree? I can cancel 1 X to -1. Then this is a 0. So very important, okay? Which point X star you are considering. Okay. For infinity, then x to -2 is little o of x -1. For the point 0, reverse. X to -1 is little o of x to -2. This is a remark number 1. Remark number 2. Remark number 2. Okay. Suppose as x approaches x star, function f approaches the number L. As x approaches x star, function g approaches number u. Then the BO rotation f of x minus L is BO of g of x minus u as x approaches x star. Implies that according to the BO rotation, absolute value of x f minus L is some constant or less than or equal to some constant times absolute value of t minus u. This inequality is true for x in some neighborhood of x star. Because of this inequality, g approaches u, f approaches L, but the convergence speed of f approaching L is at least as faster as the convergence of g to u because of this inequality. Do you agree? This is about BO rotation. Now, little o rotation. Okay. This is a B. Little o rotation. Implies that this limit x approaches x star f of x minus L over g of x minus u is 0. F is approaching L, g is approaching u, but their ratio approaches 0. What it means? It means that f approaches L faster than g approaches u. Okay, yeah, this okay implies that f of x approaches u faster than g approaches u. Right? Little o rotation. Okay. This is a remark number 2. Remark number 3. We have BO little o rotations for sequences. Actually, the sequences are only special case of the BO and little o rotation for functions. Why? Because a sequence can be viewed as a function. A sequence say xn can be viewed as a function, okay, f of n. Independent variable is N assumes natural numbers 1, 2, 3, 4, 5, 6, and so on. Okay. The function value is when n is 1, function value is x1. When n is 2, function value is 2. So f of n, the function value is xn. Okay. The domain of this function, is the set of all natural numbers. Okay, now for functions, BO rotation, okay, BO, okay. BO rotation means BO rotation means two sequences, okay. BO rotation means f n absolute value over gn absolute value less than or equal to some number for n in a neighborhood of infinity. Now n approaches infinity. Yeah, n approaches infinity. So infinity is x star. A neighborhood of infinity. That means that for n, for all n large enough. You agree? Neighborhood of infinity. That means that for all n large enough, this inequality is true. Okay. So if this inequality is true, so we say that f n is BO of g of n. Now f of n is xn. BO g of n now is yn. Yeah, as n approaches infinity. So the BO rotation for sequences are just a special case of the BO rotation of functions. Similarly, little o rotation. For functions, little o rotation means f of n over g of n. Absolute low absolute value. Yeah. Low absolute value. F of n, g of n. Limit independent variable now is n. Approaches x star now is infinity. Is 0. This is a little o for functions. Okay, now f of n is xn. Y of n is yn, is 0. So this is implies that xn is little o of yn. So the little o rotation for sequences is just a special case of the little o rotation for functions. This is a remark free. Now let me show you examples, okay, about little o and big O rotations. Example 1. By Taylor's theorem, we can expand expanding psi of x about the point 0 by Taylor's theorem. Okay. Then we have psi of x is x minus 1 over 3 factorial x to the third. First term, second term is 0. first term. No, first term is 0. First term is 0. This is second term. The third term is 0. This is the fourth term. And then plus error term. This equation is true for nx. For nx. Okay. Where the error term is 1/5 factorial cosine of sine times x to the 5th. Okay, where sine is a point. We don't know what the point is, but we know it is between 0 and x. Okay. This is from Taylor's theorem. Now let me compare. Let me compare the following two functions. Compare. F, this function is sine of x minus x plus 1/3. 1/3 factorial x to the third. And function g is x to the 5th. Okay, now take a look at their ratio. Absolute value of f over absolute value of g. The numerator of by this equation, I move the first two terms to the left-hand side. Then we can see that the numerator is absolute value of E4x. E4 is this. So this is 1/5 factorial cosine sine times x5 absolute value. Cancel x to the 5th. Then we have 1/5 factorial cosine sine absolute value. Because a cosine is always between -1 and +1. So this is less than or equal to, is constant, 1/5 factorial. Right. Because f absolute value over g absolute value log greater than 1/5 factorial, we can make the following statement. The statements. Okay. A. Sine x minus x plus 1/3 factorial x to the third. This is function f. Function f is BO of function g. G is this is a function g. X to the 5th is function g. As x approaches 0. Why? Okay. This inequality is true for any x, for x in this interval. Now, this is true for any x. Now I view negative infinity to positive infinity as a neighborhood of 0. Okay. View negative infinity to positive infinity as a neighborhood of 0. The constant in the definition, the constant is 1/5 factorial. This is C in the definition. So I can find a neighborhood of 0 and a constant of C, so that this ratio less than or equal to C. Therefore, function f is bit O of function G. So I have this statement. Okay. B, I can also make the following statement. This is function f. Function f is bit O of function G as x approaches positive infinity. Why? Now this time I will this interval as a neighborhood of infinity. Right? I can find a neighborhood of infinity. And I can find a constant. The constant is 1/5 factorial. So that its ratio less than or equal to the constant, then I can write function f is bit O of function G. Yeah. In fact, I can write function f is bit O of function G as x approaches A. What is A? Any number, any finite number, or negative infinity, or positive infinity. Because I view this interval as a neighborhood of the point A. Yeah, this is example 1. Now, example 2. Example 2. By Taylor's theorem, we have psi of x is first term. Taylor's expansion, first term is 0. Sine of 0 is 0. I expand sine about the point 0. Second term is x. And the third term about 0 is 0. And the fourth term is this. Then plus error term. Plus error term. Right? The error term is in the previous example where error term is equal to 1/5 factorial cosine of some point psi times x to the 5th. Okay. Yeah. This is
Professor.
true. Yes.
I think it should be minus 1/3 factorial x cubed.
Oh. Okay. Okay. Minus here, right? Minus. Okay. This expansion is true for any x. For any x. Okay. This is true for any x. Psi is a point between 0 and x. Okay. Now, in this example, I compare. Okay. I compare function f psi x minus x plus 1 over 3 factorial to the function g is x to the 4th. As x, very important, specify which point x is approaching. Okay, approach 0. Okay. As x approaches 0, function f approaches 0, function g approaches 0. Which one is faster? Okay, now because f of x over g of x, let me compute this limit. This is a limit f actually from this inequality. I move the first two terms to the left side, then I see function f actually is e4x, and function g is x to the 4th. Now I plug in e4. E4 is 1 over 5 factorial cosine sine x5, and then x4. Now I cancel x4. x4, 1 over 5 factorial cosine sine x. Limit is 0. Because their ratio approaches 0, we have function f is this function f is this function. Function f is little o of function g. Important, say that as x approaches 0. As x approaches 0, function f is little o of function g. Now B. How about I compare these two functions. F is sine of x minus x plus 1 over 3 factorial x to the, and g x to the 6. I compare these two functions as x approaches infinity. Okay, as x approaches infinity. Yeah, as x approaches infinity, both functions approach infinity. Which one is faster? Okay. Okay. Now let me consider the ratio. X approaches infinity. Okay. Consider the ratio. Okay. Function f is e4x. Function g x to the 6. Then e4 1 over 5 factorial cosine of some point psi x to the 5th, then over x to the 6th. Now cancel x to the 5th. 1 5 factorial cosine of sine then over x. Cosine, this function is bounded. Now x approaches infinity, so this is a limit is 0. That means that g goes to infinity faster than f. We have, no, f goes to infinity faster than, oh, no. G goes to infinity faster than F. Then, but anyway, according to the definition, F is little o of G. Okay, emphasize that as X approaches infinity. Yeah. Second example. This is topic 1. BO and little o rotations for functions. Now, second topic. Let me see. Second topic. Second topic. In these two sections, there are some theorems that we often use, but these theorems, they are all from calculus. Take a review. Topic 2. Topic number 2. Okay. Theorem 1. Theorem 1. Intermediate value theorem from calculus. Yeah, this theorem says that on a closed interval AB, a continuous function F assumes all values between F of A and F of B. If you draw a diagram, very easy to understand this theorem. Okay, X, Y axis. Okay, say interval AB is here, closed interval. Okay, closed interval including the two endpoints. At the point A, suppose function value is here. At the point B, function value is here. Now the function is continuous. The graph continuous. Okay. Then for any number between these two function values, say arbitrarily pick a number, say pick a number F. If I draw a horizontal line through number L, that horizontal line must intersect the graph of the function. Yeah. So there is a point C. You see, function value at C is L. This is what the meaning here. A continuous function assumes any value between function value at A and function value at B. Fundamental theorem from calculus 1. Now, second theorem that we often use. Theorem 2, mean value theorem. There are two mean value theorems. One is for derivative. The other one is for integral. Okay. Yeah, this is for derivative. If function F is continuous, the graph is continuous on a closed interval AB, and derivative exists on open interval AB. Let me draw a diagram. Okay. This is an X, 0, Y, Z, interval AB here. The graph is continuous, derivative exists. Not this graph, because this graph has a corner, and a corner derivative doesn't exist. So not this graph, okay? This graph is not smooth. It has a corner, not smooth, okay? This case, AB. Function is continuous, graph is continuous. Derivative exists. That means that the graph should have low corner. In other words, the graph should be smooth. Smooth. Low corner, okay? Then there is at least a point. So let me call the point psi in the open interval between A and B, such that derivative as psi, derivative is slope of tangent line, is equal to f of B minus f of A, then over B minus A. What is this number? What is this number? This number is, if I join the two endpoints of this curve with a line, two endpoints, now with a line, then the slope of this line is this number. This theorem says that between A and B, there is a point psi where the slope of the tangent line is equal to the slope of this red line. That means that two lines, their slopes are equal. Those two lines are parallel. That means that between A and B, we can find a point psi where tangent line is parallel to the red line. Which point? Yeah, see, I can find here. Yeah, draw a tangent line. This tangent line is parallel to this line. Okay, this point here is psi. Mean value theorem for derivative. The next theorem is Rolle's theorem and mean value theorem for integrals. But I don't have time to present these two theorems. All these theorems are fundamental, all from calculus, but we often use them in this course.